These wheels have largely been manufactured the same way forever. They're cast, generally cast as a single piece. And then there's a wear band at the surface that's just been heat treated and quenched, and it gets machined down as the wheel wears out in use. And once it's been worn out, the whole wheel is scrapped. So there's actually only, depending on the wheel and the surface, a little over an inch of functional material that will actually see a track in the whole lifetime of the wheel. And the whole rest of that half ton of steel is then scrapped and remelted. So I ran some numbers. It's about 53 kilowatt hours of power just to melt the steel to cast one of these wheels. Every car on a train has 8 wheels. In a 100-car train, it's 4 years of your household energy consumption just to just to melt the steel to make these wheels. So there was a huge incentive to try and optimize this process. There's been interest in trying to do what seems like an obvious solution to a lot of us, weld something onto that wear surface rather than just casting the part for years. But that came with its own set of issues, which was that the wheel is intended to fail. So you put tracks out in places like that, all across North America especially, and if I go and I hard face this wheel, which a lot of the people I talk to back home in the resource extraction industry are like, oh, you want your wheel to last longer, you throw a tungsten carbide in it, and it'll last forever. Well, but then I've turned my wheels into moving grinding discs, and the poor tracks are gonna be gone in a year, and nobody wants to go out and put new track down out there. So that led the project to sort of a unique set of specific requirements for anything we were gonna do to fix these wheels or to repair these wheels. And that's needed a compatible hardness. So whatever we put in this wheel has to have a similar hardness to what's in the wheels as they're manufactured. So we're trying to match to the rail and be slightly softer. Then also, the way they then improve lifetime without going for hardness is residual stress. Like I said, there's a heat treat and quench on the rim, and that sets up a significant compressive residual stress in the rim of the wheel, and that's what gives it most of its lifespan. And then of course I need to meet those two things with an alloy that I can actually weld into this giant steel, 1070 carbon steel disc. So that comes with a whole set of challenges. And so the reason this project came to us, and the reason there was some optimism about it, was because several years ago, another student in our lab did this experiment where they were working on repair of a downhole part for an oil and gas company, and they were doing welded overlays to try and repair the part when it came back from service. So what you're looking at here in this table is a set of fatigue test results. They put it on a rotating bender, ran it till failure. So the numbers at the bottom, we're not going to worry too much about the specific numbers, we're just going to look at magnitudes. But basically the number at the bottom is 25 times 10 to the 4. It's the number of rotating bend cycles to failure for each part. So that first one I just boxed is the control. That was the as-cast part from manufacturer, its lifespan. Then they tried welding it. And they were putting on like a 13 chrome alloy steel, and when they welded it, it didn't work very well. Yet, you know, a little bit more than half the lifespan. It's okay for repair, we can live with that, whatever. Then they preheated it to 300 degrees, and it outlasted the part as manufactured by almost double the lifespan. So that was weird. Okay, preheat helps. Maybe we keep going, we'll preheat to 600 degrees Fahrenheit. It got worse. So preheat helped, then it made it worse. What's going on? They published this data. They basically told the guys, yeah, we can repair it, preheat to 300 degrees, you're gonna get a great lifespan, and they kind of moved on. And I've looked through the topics for today, and so some of the people here will know about LTT alloys. So at the time when they did that and they got those weird results, this is what they thought they were getting. They didn't really understand a lot about it, but they knew that there are certain alloys, most of us know this, that when you weld them, they go through their martensite phase transition later in the cooling curve, and that later transformation is associated with a phase expansion. And that phase expansion can have beneficial residual stress impacts. The problem was, and in my time reviewing literature, I find a lot of this, no one is able to give you great recommendations for how late of a transition is late enough. What kind of preheat is a sufficient preheat? What amount of transformation is enough transformation? So that meant we had an idea, but nowhere to go with it. So now I gotta take a little detour into residual stress here because I've got this fancy plot next to me. And we're gonna be talking about that for a lot of this. So for people who really understand residual stress, this next bit's gonna seem kind of silly, but let's make sure we're all on the same page. So we have a plate, right? We weld on it, that's that first point on the graph. The weld starts heating up, it gets bigger, right? So that's there. And so what happens, of course, you start welding on a plate, the weld wants to get bigger, the plate doesn't want to get bigger. Eventually, as the weld gets bigger, constrained by the plate, it's experiencing compressive strain. it's gonna keep elastically deforming until it yields, and then that's that second point we just hit. It hits plastic, it yields, and now as it keeps expanding, it's plastically deforming until we get to this point. This is our peak temperature. We start cooling down. Oh no, our weld is bigger than it used to be. When it tries to cool down, it pulls on the plate, and we end up in a very high tensional residual stress. And this is what makes welded plates smile at you. So we know this is pretty standard, but that LTT alloy, it does something like this. So we can use that phase transformation strength. So if you look at my second plate there, now it's that weld metal, when it went into the martensite phase transformation, it expanded, and now it's under compression because it's trying to be bigger than it was prior to welding, right? So you can see that it's dropped. So like I said though, it's nice to put it on a graph. How do we make any actual functional use of this? So from here, I'm just gonna look at this plot. This is just sort of that last half of what I just showed you, right? We're coming in cooling, we hit yield on the way down in tension, and then that is epsilon yield is the tensional yield strain of the material. So these little plots here, pull this guy up. So this T end is the thing we're gonna look at, right? So this is the thing we care about, right? That's the temperature at which the martensite transition finishes. And ultimately, what we've established happens most of the time in most welded materials is you transform to martensite, and then you keep cooling down, and you just yield again, and you're back in tension. And because the final residual stress state depends primarily on the strain experienced before reaching equilibrium temperature, it doesn't matter when this happened or how much it happened. If you hit this yield tension force again, you're back where you started, you're in tension, things want to crack, right? So what we said is, well, we can look at this. If it's just based on this recontraction cooling, which was the thing we decided to try looking at, maybe that's all it is, then what we can establish is that if this is the temperature the martensite transition finishes, then all I have to look at is how much phase strain was there, how much phase expansion occurred as a result of the martensite transition, and then at what rate does it recontract until we hit tension again. And so we can see that from just looking at this, we can get a really easy answer. If this is the amount of phase expansion we have, which is easy to get, it can be simulated in JMAP Pro, you can find it from a Sato test, it's also like a known value for lots of materials, and I know my thermal contraction coefficient, then I know exactly if I want to retain some of this, if I don't want tensional residual stress after my weld has reached equilibrium temperature, I just need my equilibrium temperature to be higher than the martensite finish temperature, and this thing I call delta T crit, which is just the ratio of the amount of phase expansion to the thermal contraction coefficient. So we're gonna try to use it. So it's okay, I've got this idea, this is how I think we can control for residual stress, so I think we can predict what these LTT alloys do. We think this was an LTT alloy, we think that's why it exhibited this behavior. Let's see if we can predict it using this model. So I grabbed a whole bunch of properties of that metal they used. Like I said, it was a 13 chrome low alloy steel or high alloy steel. I grabbed all of this out of JMAP Pro. So there's our martensite finish temperature, the phase strain over the thermal contraction. So I have 279 degrees Fahrenheit of cooling that I'm allowed to use between reaching the martensite transition completion and equilibrium temperature. So we look at our preheats. So that gets me 111 degrees Fahrenheit. So if my equilibrium temperature is higher than 111 degrees Fahrenheit, I'm gonna get some benefit from that phase transition. So we got three cases. We got 300 degrees Fahrenheit. That's right in our sweet spot. We're above that critical temperature. Then we got 68 degrees Fahrenheit room temp. That obviously is well below, so it should be bad. And then we've got 600, and 600 is kind of unique. It's actually above that martensite finish temperature. So something weird is gonna be happening there, but we'll look at it. So let's look at those three cases. Like I said, 68 degrees Fahrenheit, we're outside of our critical allowed temperature, and it's exactly what I showed you earlier. The martensite transformed, and then it contracted and it yielded, and we're back where we started. We might as well have not had the transformation from a stress point of view. But then we've got this one in here at 300 degrees Fahrenheit. We've completed the martensite transition. Also for metallurgists who want to be upset with me, 95% martensite is what I'm calling complete here. But so complete transformation, and it contracted a little bit because we're past that martensite finish temperature, but not enough to reach that critical stress that I talked about. And then 600, we have to actually now look at the transition. We're past the start of martensite formation, but we didn't hit the completion. So while it probably still proceeded to complete the martensite transformation, there was no strain developed because there was no thermal gradient. So that stress just sort of gets absorbed. So there's our three conditions. We got our 68, 300, 600. Now we're going to look at how it compares to that fatigue resistance we saw. So our first one, you can see I ran all the numbers to get what this actual strain would be. It's very easy to figure out, right? It's that epsilon phase over alpha is the slope of the curve, so then you can figure out the actual strain. So 0.23% strain, and look at this, 24% reduction in fatigue life. So we look at the next one, okay, 42, we have a minus 2.8%, so that's 0.28% compressive strain, so we should see a pretty good improvement here. 67% increase in lifetime. But what really surprised me when we started running these numbers is then for the 600 degree case, I used the data out of JMAP Pro to find what percentage of Martensite transformation we were at, like how far had we proceeded when we hit that equilibrium at 600 degrees. Well, it's about half of the 300 degree, and sure enough, the increase in lifetime is about half as much. So using this very simple, just slope-based model, I'm predicting with pretty good accuracy what the improvement in fatigue life under the same alloy would be. So then to bring it back to my train wheels, now that I validated, like, okay, there seems to be something here that's working, we went to the train wheels. So this is how I actually apply this model when I'm now designing things for these wheels. So there's sort of two design routes you can take when I apply this now. The one I'm using is over here, and we can't preheat a half ton of steel effectively. If I wanted to weld repair all 8 wheels on every car of an 800 or of a 100 car train, I'm not preheating all of them to 300 degrees. So I have no preheat. So my selection of preheat, room temperature. I need whatever material I choose, it has to retain some of that compressive residual stress when I make it to room temperature. So I know that. So that determines that T Martensite finish and that delta T crit. So I know the temperature that Martensite completes and the range of temperatures I can work within to get that benefit. And then from there I know the material properties I need in my alloy. And then from there I did a bunch of simulation and I wrote some codes that allow me to pump simulation back and forth with alloy design. And I can design an actual alloy, and that's what's going down in these train wheels. And then just to sort of help explain how this can be used from like weld designers and welding engineers, you can do it in the reverse direction much more easily. If you know what alloy you're welding, regardless of the alloy, it doesn't even necessarily have to be classified as LTT. This would work for anything that undergoes a phase transformation. Then you know the material properties of it. It's easy to determine that TMF and T crit, and then you know exactly what preheat would get you the optimal residual stress. And of course, if you think back to that plot I showed you, the answer to this is actually quite simple. The optimal stress would be as close to the Martensite finish temperature as you can achieve. So in terms of application, I've now put these alloys down into these wheels. And for perspective on how well this has been working for me so far, this project was undertaken with this company with another research lab a couple of years ago. They were doing submerged arc welding of wire-based consumables. I'm doing plasma transferred arc with powder-based consumables, which is allowing me to design these alloys to have these transition temperatures. They made a series of 13 welds and all of them cracked in deposition. I have managed to put a full deposition through that rim without cracking a deposit yet. And I'm attributing that primarily to the fact that despite the really high cooling rates that occur when you're welding on this much steel, that compressive residual stress I'm retaining in transformation is preventing cracks during overlay and letting us get through to a heat treatment or sometimes not even needing the heat treatment later. And then also, my hope going forward with this is right now I'm just predicting that amount of strain, but going forward we'd love to be able to extend this I think fairly easily to predict the complete tendon force of any weld that's undergoing this transformation and include phase transformation stresses in existing models for the tendon force. So hopefully at some point you'll see one of my welded wheels on a train and we can say that we've actually helped somebody with all of this math, but that's really it. I wanted to thank Amstead Rail. They've been the one supporting a lot of this work and allowing me to do a bunch of math while also fixing their train wheels for them. Yeah, thanks so much. If there's any questions.
We have time for a couple of questions. Does anybody want to ask Carter something?
When you guys would do the repairs, would that be on site or would that be in like a lab setting, like a fabrication setting?
Yeah. Right now, so right now we're doing obviously in lab, but when we talk to the company, they're interested in both. Obviously, like the pipe dream for this would be like a train car rolls over like a drop station. You drop the whole truck axle out, take it over. You've got like a PTA machine that slams the material in, little lathe, take it off, put it back on the car, keep going. Obviously, that's the dream, but like right now, I'm like, maybe I can weld in a wheel. It's a lot of steps to get there.
So, for then the preheat, are you tracking down to like 0, or like how low are you at
We're looking, so that's an interesting question. So right now we're just looking at like room temperature, so like 68 to 70 something, right? Ideally, when you get to the alloy design, because a big part of this, when you're PTA welding these, I'm putting down, we're filling almost a ½ inch cut out in this wheel. So, and this is the thing, you notice I mentioned equilibrium temperature instead of room temperature, and it's because when you do this PTA weld, you actually lift the equilibrium temperature, sometimes up to like 100 and some degrees. So that's part of what we're using to get a useful number here, is I'm able to, sometimes I can do simulation, sometimes you can do it just through like heat input times mass. You get an equilibrium temperature that's sometimes up to 100 or more degrees higher, and then your transition temperature can be cheated up a bit. So.
I'll ask you a quick question. There's a good chance if you have to fill up a ½ inch that you're going to be doing a multi-pass weld. How do you think that's going to play a role in your residual stress profile?
Yeah, so in terms of the overall profile, there's going to be an impact. The hope right now, when we take micrographs of some of the welds we've done, you get a lot of martensite through the whole thing. So my hope is, and again, looking at further work, I would love to see if this extends to, if I have an existing material with these properties, when I sort of like temper beat it, like when another weld comes over, how much of it transforms again? And do you retain this benefit through all of those welds? In which case, if it does, you could end up hoping to see a compressive residual stress being set up through the whole depth. But obviously, some of it's going to be tempered, like become tempered martensite, and you're going to lose it. Like I said, the goal here in some ways was maybe you get compressive residual stress, maybe it just lets me weld on something that would have otherwise cracked to pieces. So you don't necessarily need to retain a really high degree right to the end if all the welds stick and it can survive into a heat treatment.
Awesome, thank you.